Hello everyone. In this video, let's learn how we can design a synchronous binary up counter that counts from 0 to 7. So 0 is the first state, 1, 2, 3, 4, and then after this, it'll go back to the initial state 0. So since we have from 0 to 7, we have 8 states. So that means we need 3 flip-flops. And we saw that in previous lecture, so we can do log 2 of the number of states, 8, and this will be 3. So that means we need 3 bits also. So the first step in the design process is to start with the state transition table. So let's list here the current state, and let's call them Q3, Q2, and Q1. And then the next state, let's call them Q3 plus, Q2 plus, and Q1 plus. So it starts at state 0, and 3 bits, that's 0, 0, 0. And then the next state is number 1. So in 3 bits, that's 0, 0, 1. And now this become our current state because we are at this state. So this here will become our current state 0, 0, 1. And then the next state, it will go from 1 to 2. So 2 is 0, 1, 0. Now this become our current state 0, 1, 0. And then the next state is number 3, which is 0, 1, 1. Now this become our current state, and then the next state is number 4, which is 1, 0, 0. Now 4 become our current state, 1, 0, 0. And then the next state is 5, which is 1, 0, 1. 1, 0, 1 become our current state. Now the next state is number 6, which is 1, 1, 0. Next state, this become our current state, 1, 1, 0. And then the next state is number 7, which is 1, 1, 1. Now this become our current state 1, 1, 1. And then from 7, it go back to 0. So this is 0, 0, 0. So next, what kind of flip-flops we're going to use to design the circuit? So let's do it with T flip-flops. So T toggle flip-flop. So we're going to figure out the inputs of each flip-flop. So let's call them T3, T2, and T1. So for T3, we're going to look at Q3 and Q3 plus. So since both are 0, so no toggle. So that means T3 is 0 in this row. So next row, no toggle, no toggle. So the next 2 rows, T will be 0, T3. So that's 0, 0. And this row, Q3 is 0, Q3 plus is 1, so T is 1. 1, 1, 1, 1, and 1, 1 for the next 3 rows. That means no toggling. 0, 0, 0. Last row is going from 1 to 0, so toggle is 1. So next, to fill up T2, we're going to look at Q2, current state, and Q2 plus next state. So now we have obtained the required inputs for the flip-flops. Now, next we can design the circuit. So let's do this using K-maps to get the minimal Boolean expression for each one. So let's start with T3. So we have 3 inputs. So we have 3 bits, so that means we need 3 variables K-map. So for T3, let's do it here. Okay, so on this side, let's have Q3. And then on this side, let's have Q2, Q1. So Q3 could be 0, could be 1. And then Q2, Q1, we're going to have 0, 0, 0, 1, 1, 1, and 1, 0. So let's look at T3 where it's 1. So it's 1 in 2 locations. And this location here, which corresponds to 0, 1, 1. So that's 0, 1, 1, it's 1. And then another location, last row, correspond to 1, 1, 1. So that's 1, 1, 1 in this area here. And then the rest are zeros. So now let's group ones together. Very easy, only in this area here. So Q3 is changing from 0 to 1, we're not worried about it. And then we have Q2, Q1 are both 1s. So now we can write T3, let's write it on this side, T3 is equal to Q2, Q1. Next, let's do the same for T2. So similarly, on this side is Q3, and then on this side Q2, Q1. So let's look at where T2 is 1. So it's 1 in this location here, corresponds to 0, 0, 1. So that's 0, 0, 1. Next is 1 in this row here, corresponds to 0, 1, 1. So that's 0, 1, 1. Next, it's 1 in this row, which corresponds to 1, 0, 1. So that's 1, 0, 1. Lastly, last row, which corresponds to 1, 1, 1. So it's in this area here. And then the rest are zeros. 0, 0, 0, 0. So obviously we can group these four together. So from here to here, Q3 is changing, so we don't list it. And then from here to here, Q1 is remaining 1. So that means we can write the Boolean expression for T2 as equal to Q1. And then for T1, it's 1 all the way, so that means T1 is equal to 1. So next we can take these three equations and design our circuit. So let's do that. We have three flip-flops. Let's assume this is T3, T2, and T1. So each flip-flop has T input. This is T3, and this is the clock. Let's assume we have rising edge. Similarly, here we have input T2 and a clock, T1 and a clock, and then each one has an output Q. So this is a Q3, this is a Q2, and this is a Q1. Those are all the clocks. And since we're designing synchronous circuit, all the clocks are connected to a common clock input. So T3 is equal to Q2 times Q1. So for times we need an AND gate. The output is T3. And then we need a Q2 multiplied by Q1. So we can get Q2 from here. And a Q1 from here. And then for T2, T2 is equal to Q1. So this is a Q1, we can take it from here. And lastly, T1 is equal to 1. So this is 1 over VCC. So this is the circuit for a that counts from 0 to 7. So on each edge, on each clock edge, each flip-flop will store 1 bit. So when we start at 0, 0, 0, so nothing is detected. If we have one clock edge that is detected, so this will be 0, 0, 1. So 1 will be stored in one of the flip-flops. On the next clock edge will be at 0, 1, 0, and so forth. And when we get to 7, it'll start over. I hope this was helpful. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.